Hello, today we're going to look at topic 3.2, part 1. We've split this lesson up into 2 days. Today we're going to focus on sine, cosine, and tangent and make sure that we understand what these ratios are. We're going to introduce a little bit of new terminology that we'll be using through the rest of the course. So let's just get started. In this course so far, as I'm sure you've realized, that we have been defining and looking at things from a different perspective than you might have seen in past classes. We're working on building some concepts that we can generalize the method that will allow us to see other things in this topic through a little bit different lens, but to be able to still understand what we're looking at. So let's start by talking about the fact that math is a technical language. So we use few words to convey a lot of information. And so one of the combinations of words you might hear referred to is standard position. So let's break that down. Standard position is the way an axis is placed on the coordinate. So it's in the coordinate plane and its angle, or when an angle lies in standard position, it means that its vertex is at the origin and we have one ray that lays on the positive x-axis. So if you will, think about if I come down here and I'm on the coordinate grid right here, and I have both lines of my ray are right here, okay? The ray that's on the x-axis is called the initial angle or ray. And then the two of them are right here. And then one of them is going to start opening and moving around the graph in the counterclockwise area to some place where it's going to stop. And that place where it's going to stop is what makes it be called the terminal angle. So it terminates there. So when we're talking about this angle, so they originally start together on the positive x-axis, and then one angle opens counterclockwise away from the initial angle, and wherever that side of the angle stops is the terminal ray. So the terminal ray, definition 2 here, is the second ray of an angle in standard position, and that's the position of any standard angle. So it would be vertex at the origin, a initial side on the positive x-axis, opening away from that positive x-axis, and wherever that ray stops is the terminal side. And that means we can define the ray as this distance between the initial side and the terminal side. And so oftentimes we'll give it some sort of letter, and so we're going to call that theta. You're going to get accustomed to working with lots of Greek letters in this topic because sometimes we're looking at more than one angle in a picture, and so we don't want to call them all by the same value. And to keep it from getting confused with something that might be plotted on the x-axis or the y-axis, we tend to use Greek letters to represent that angle. So here are a few of the Greek letters that we typically use. There's a whole lot of them, and they get used for different things. A lot of time you'll see Greek life in college. They have different sorority houses, fraternity houses that are named through the Greek letters. Here, the ones we use the most are alpha, and it looks like when I write it, these are all nice and pretty and tight, but when I write it, it looks like a little squishy loop-de-loop on the side. Gamma is the loop-de-loop on the bottom. We are now using theta. If you are to put your calculator in trig mode, when you press your X button, you will not see an X when you're in this mode. You'll only see a theta. So on the calculator, theta will represent our angles. What else? Sometimes you might see the U that looks like this. Beta, so it's a B with a little tail. You've been using pi since geometry. We use the sigma notation when we learned about sequences this year. And every once in a while, you'll see this omega, this little kind of curvy looking W. Those are probably the most common. Obviously, there's more Greek letters, but we just kind of have some that we favor a little bit, and we tend to use those. And that way, when we're defining the angle, we don't get it as confused with the distance by using a little different notation. All right, so hopefully now everybody understands what standard position is. So if you see standard position in any part of the description, then you have an idea now of what that looks like, and you should be able to visualize what's going on there. Okay, so let's look at the ratios. So the first one, sine, cosine, and tangent. First off, let's talk about all of these are going to be angles in standard position. So as we look at these values, they're angles in standard position. The circle is centered at the origin. There is a point P, and that is where the terminal ray intersects the circle. Now think about the very first day we did our radian and degree activity, and we measured in terms of radians, and then we took and connected it, and we made this angle here in the middle. So that's kind of what we're talking about. So the first one is sine. So as you're looking at this notation, keep in mind that you need to have the trig name, so sine, cosine, tangent. Then you need to have an angle marker right here before we set up the ratio. So all of these are ratios that are going to happen in this triangle. Okay? So the ratio, which just means something divided by itself, for sine represents the vertical displacement of P. So here is my horizontal axis. Vertical goes up and down. So we're talking about this distance from that horizontal axis up to the point. And then between that and the distance from the origin to the point. So now we're talking about that. So sine is a ratio of those two things. And the actual ratio is y over r. So that's the displacement, the vertical displacement over the radius. So this is the sine ratio and what it means in terms of our picture right here. So vertical displacement and the radius. The next one we're going to look at is cosine. So if you look in this circle, think about the Cartesian coordinate on the bottom. That's just the square graph you learned to graph on beginning by probably middle school, algebra 1 at the very latest, where you would start at the origin and you would plot the point 2, 3 by going over 2 and up 3, or the plot negative 2, 3 by going to the left 2 and up 3. So as we look at this, that axis down there kind of represents the coordinate plane, and then we have set a circle on top of it where the origin or the mark in the center of the circle is lining up with the origin on the x-axis. Okay? So when we plot, we're not just plotting in a square, but we're actually plotting a point to the left and up that happens to fall on the axis. All right, so that's kind of just going over a little bit of background there. And so if we do cosine now, cosine of theta, then that is the ratio of the horizontal displacement of P to the distance between the origin and P. So the horizontal displacement. Now I did put the X up here for the horizontal. It's going from the vertical axis to the ray, to the terminal side. But if I put it down here, you couldn't see it on the axis. So when we look at the ratio cosine of theta, it's going to be x, which is that horizontal displacement over the radius. So this is just showing you when I say horizontal displacement, horizontal will come from the y-axis and the line is horizontal to the terminal ray. When we talk about vertical displacement, we're coming from the x-axis up or down to the point, so we get this vertical distance. So we have the horizontal displacement to the distance right here. So big enough so you can see the orange there. And so we're talking about that. So what this means right here is this is saying the angle that has a sine value of this ratio, the angle that has a cosine value of this ratio. Okay, the last one that we're building our knowledge of here is tangent. And tangent theta is actually the slope of the terminal ray. So it's the slope of this line. And how do you find slope? You take the vertical distance and you divide it by the horizontal distance, right? We learned that slope is y over x. So that means if tangent is the slope of the ray, it's also the ratio of the vertical displacement to the horizontal displacement. So the vertical displacement to the horizontal displacement. And that's the distance between the origin right here and where that P is. That's that slope of that line. So the displacement would be the horizontal and the vertical. And it can also be the slope of that line. Okay, so the thing about tangent is it has more than one ratio that we can use to define it. We can do y over x, the vertical displacement over the horizontal displacement. But we already talked about the vertical displacement. The vertical displacement is happening on the y, and that's associated with sine. So I can also say sine divided by the horizontal displacement, which is the cosine, and I can take the sine value divided by the cosine value and get the tangent as well. And which we use kind of just depends on what we're doing with the problem. Okay, let's take a look at our first example. I want you to pause your video and then I want you to do your first and second read for the problem. And then I will give you a few more instructions before we decide which answer we're going to pick, A, B, C, or D. So go ahead and pause your video and do your first and second read. Okay, so hopefully you've done your reads there and you've marked up your problem. And as we're doing this, we made a note that it's a circle at the origin. It tells us that theta is in standard position. So this distance from the initial to the terminal is theta. And it says that it intersects at point P. So we're looking at this point, which is an XY coordinate. And then it says which of the following is true. So that's all the information you get out from the problem itself. But don't forget we need to look at the picture as well, because this point right here from the origin to the edge of the circle is the point 3, 0. And 3, 0 is telling us something about the radius. Remember, from the center to the edge of the circle is the radius. So if this goes from 0 to 3, then the radius is 3. Why is that significant? Because there's an infinite number of radii in a circle, and they all have to have the same measure, and they all have to be equal, so it's 3, which tells me that this ray on this triangle right here is 3 as well. Okay, so keep that in mind, and then we're going to be using this cosine ratio, our information from our circle, and then we're going to go through these choices, A through D, and we're going to pick the right one, and going to give a reason on the others as to why we're eliminating them. So we're thinking about the radius, we're thinking about the displacement, and the ratio of cosine. So go ahead and pause your video, figure out which one you think is right and why, and then have a reason for eliminating the other three. Pause your video. Okay, let's see how you did. So the ratio for cosine of theta is x over r. If r is 3, then cosine of theta should be x over 3. And I can find this ratio right here in the first part, and it talks about the horizontal displacement of P from the y-axis to the distance between the origin and P, which is the radius. When I look at choice B, I eliminate it because in the top it's talking about the vertical displacement, not horizontal. C, I would have eliminated because that's actually a tangent ratio. This is showing the vertical displacement to the horizontal displacement. And the only time we see that ratio is in tangent. We looked at this one right here. And then we eliminated choice D because we have our radius in the wrong spot. We have the radius on top over the horizontal displacement on bottom. Okay, so let's look at example 2. We have a circle and it has a radius of 5. So we know that 1, they tell us right here, but 2, because it goes 0 to this coordinate, which is 5, 0, then that means this radius here has to be 5, which also means the radius here has to be 5. Okay. So then it says it is centered at the origin and the angle of measure theta is in standard position. The terminal ray of the angle intersects the circle at point P. So remember, in standard position, this P would have been lined up with the positive x-axis, and it would start opening up this way and going around until it stops. Where it stops is the terminal side. Okay, so let's look at example 2. In this example, it tells us in the problem that it is a circle with a radius of 5, centered at the origin with an angle measure in standard position. So when I look at this, I could have got this from the picture as well because it tells me this coordinate point is 5, 0. That means the distance from 0 to that point is 5. And that means this line right here is 5 as well. Let's get that off there. We need that. All right. So that's our radius right here. And it tells us that this angle is intersecting the circle at point P. So we're talking about the angle that starts here and goes all the way around to here in the positive direction. Okay? So now we know that we have this point P, but we don't have any coordinates for the point P. We do, however, have coordinates up here for 3, 4. And I can use my reflection property to figure out these points. If I wanted to reflect this point up here that's 3, 4 down to position P on the circle, what would the new coordinate be? What would the coordinates of P be? And that would be 3 comma negative 4. Because if you think about plotting a point, right, we would go in the positive direction and up to this point, and here we would go to the positive direction and down to this point. And anytime we plot those points, then we can use the negative and positive directions to get us there. All right, before we do anything else, let's talk about some things that you should already know coming into this about graphing points. So pretend we're talking about the Cartesian coordinate plane, the square plane that you've been graphing in for Algebra 1, 2, and Geometry. And everything in this quadrant is labeled Quadrant 1. Everything in this piece of the graph right here is Quadrant 2. Everything in this part of the graph is Quadrant 3. And everything in this part of the graph is quadrant 4. So oftentimes when we talk about the quadrants themselves, we'll use Roman numerals. That helps us keep that distinguished between values in our problems. Or sometimes you might just say Q1, Q2, Q3, Q4 to represent quadrants. But you want to do something so you don't get confused with those numbers in the problem itself. Okay, so now that we have these points, then I know that I have a horizontal displacement of 3 and a vertical displacement of negative 4. So I want you to pause your video and we're going to use the ratios and then find those equivalent ratios in the circle. So I don't have to flip back and forth, let's just go ahead and write them in together before you pause. So sine is the vertical displacement over the radius. Cosine is the horizontal displacement over the radius, and tangent is the vertical displacement over the horizontal displacement. So using those ratios, then I want you to determine what is sine of theta in this situation. So go ahead and pause your video. Okay, so let's see how you did. So in this case, 2 point P, the vertical displacement is negative 4, and then the radius is 5. For cosine, the horizontal displacement is 3. The radius is 5. And then tangent, the vertical displacement is negative 4, and the horizontal displacement is 3. So when we graph that point in the Cartesian coordinate, we would go from the origin, we would go over 3 and then down 4. So that's how we go about that. You could also see this one with the negative pulled in front of the fraction. And same for tangent. So either one of these would be acceptable. Leaving this in the problem does give you a little more visualization as to what part of it is in the negative direction. If you're given something like this and you're told that it is in the fourth quadrant, then you would have to say, okay, if it's in the fourth quadrant, then I know that the vertical displacement is going to be negative because I'm not going to have a negative radii. All right, so we have looked at our quadrant markers. Let's go back and think about what would points look like. If we were going to graph a point in this quadrant, we would go to the right, which would be positive, and then we would go up to wherever the point is, and that would also be positive. So every time I graph a point in that first quadrant, it's all going to have positive values. If I graph a point in the second quadrant, then from the origin, I have to move in the negative direction first, and then up to a vertical direction, or up in the vertical direction. So this would be negative for the horizontal displacement and positive for the vertical displacement. If I wanted to plot a point in the third quadrant from the origin, I would go to the left, which is in the negative direction. Then I would go down, which is also in the negative direction. So all the points in this quadrant are going to be negative, negative. And finally, in the fourth quadrant, we would move to the right of the origin, so that's positive, but then we would have to move down to the negative part of the graph. So this would be positive, negative. And so all of the points that are plotted in this quadrant will have these signs with them. All of the points that are plotted here will have these signs. All of the points in this quadrant will have these signs, and all of the points in this quadrant, quadrant 3, will have this sign. Okay, so that's just another little layer upon information that we know. All right, so let's move on to the second part of example 2. We have a graph here, same graph, except we don't have any values. So we have point P here, which has the coordinate point x, y. So let's do our first and second read in the problem. So this is a figure with a circle with radius centered at the origin in standard position. The terminal ray of the angle intersects point in point P. So here's my terminal ray. So theta is from here to here. And then the coordinates that we're going to use are x and y. Then I want you to find the points Q, R, S as a result of reflecting. So we're going to take point P and reflect it over to point Q, which is going over the y-axis. So if you go over the y-axis, what's going to change? You're moving in the negative direction, now, which is the horizontal displacement. So when you look at a point over here, remember we said they were going to be negative, positive from this part of this example. So down here, then when I use my x and my y here, it would be negative x that have a positive y. And that's going to be the coordinates for point Q. So go ahead and pause your video and find the points for R and S. All right, so how did you do? So when we reflected from this to the second quadrant, the x became negative. When we went from Q and reflected over the y down to R, it would still be in the negative direction and the negative direction, so they would both be negative. And over here, when we reflect R over into quadrant 4 for your S point, then you would graph positive and then down to the negative. So think about it this way as you're looking at this little triangle. So here's the terminal ray. So here's my angle. If I drop that down to the x-axis, I make this little triangle here. And if I plot it, I would do positive going to the right of the origin and positive going up. But if I'm going here, this amount of space or this distance is in the negative direction. And then when I went up, it was positive. And here, once again, in the negative direction, but here it's also in the negative direction to get down to R. And now we're going to go in the positive direction to get over to this point and then down in the negative direction. So that just keeps tying what we know about the negative and positive values in the quadrant to actual X and Y points that don't have any numbers for you to use. So you have to really think about what that means. All right, so let's go ahead and take a minute and put the coordinates down here so we have them nice and handy to look at when we do example 4, 5, and 6. So for example 3, we're just getting the coordinate points. So point Q then would be negative x and y, and point R would be negative x, negative y, and then point S would be x, negative y. Okay, so that gives you your vertical and horizontal displacement. So what I would like for you to do in the last part here is to find the sine ratio at point S, the cosine ratio at point Q, and the tangent ratio at point R. So using your points that you found here when we reflected them around and your ratios from the front side, answer the question by writing the sine and what that sine is doing at point S. So go ahead and pause your video one last time. Okay, let's see how you did. So in this one, sine of theta has the horizontal or the vertical displacement over the radius. And so when I look at my point, I'm going to have negative y over r. Or you could have that a negative in front of the fraction. You could pull that in front like right here and make the whole thing. If you are going to be working a problem and you have to interpret some of this about where to plot something, you're going to have to make some decisions as to where you want to put that negative. And it would depend on what trig function you're graphing and what quadrant you're being asked to graph in. All right, so example 5, cosine. So cosine of theta is going to be, in this case, negative x over r, or we can put that negative out in front, so it looks like that. So remember what this means. This means the angle that has a sine value of this ratio, an angle that has a cosine value of this ratio, a tangent, an angle that has a tangent value of this ratio. All right, so then when we do tangent, remember that is the slope of the terminal terminal ray, excuse me. And then it is also the vertical displacement divided by the horizontal displacement. So those are things that we know about tangent. So then when we actually get the ratio for tangent, it's going to be negative y over negative x. And then that's also y over x. So thinking back to our triangle here, I have a question for you. In which quadrants would tangent of theta have a positive ratio? All right, in which quadrants would tangent have a positive ratio? So what we're thinking then is we're looking at the different quadrants and we're trying to figure out when would the vertical displacement over the horizontal displacement equal a positive number. So hopefully you could see that that's going to happen here because the vertical displacement and the horizontal displacement are both positive. And then again over here, because the horizontal displacement is negative, and I'm sorry, the vertical displacement is negative and the horizontal displacement is negative, and a negative divided by a negative is a positive. And that's what we found right here when we were talking about this. So knowing this characteristic of this displacement and that it's y to x, we were able to answer some questions about, I'm looking at this graph, when could I have a tangent value that would be positive? It's going to have to occur in one of these two quadrants, quadrant 1 and quadrant 4. So we've talked a lot about the ratios themselves. We've talked a lot about how when we reflect these things over, that we can interpret what's going on with the displacement on the circle based on just plain old graphing like we started doing and have been doing ever since Algebra 1. We have definitely recognized and reviewed how to write the quadrants because it has been a while, probably since you talked about them. So we know how they're numbered, and then it goes counterclockwise when you number. We have talked about in what quadrants the displacements would be positive and negative, and we tied that back to how we would graph points in that quadrant. And then we learned that reviewed, if you go from the center of your graph to the edge, that's still called a radius. And so sometimes we can find the radius out by looking at that coordinate point. And since that distance is 5 to here, when I move my angle started here, when it moved around and terminated here, that termination is going to go all the way to the edge because that angle is intersecting the circle at point P. So remember that this point all the way around here is angle theta. There is a connection that some of you may already be aware of this part of the graph right here. So this little piece right here does have a connection to the big graph as well. And that's one of the topics we're going to be discussing in the next part of the lesson. So what I would like for you to do today is go ahead and work on your daily practice. I gave you a worksheet today to practice these topics, concepts, skills, vocabulary. Make sure that if you have a question, you mark it on your worksheet so that we can address any of that as you come to class next time, because sometimes you do the work now and it's a day or so before you come to class and then you forget all about it. And it is very important that you're keeping up with your work because as we're building new skills here, they are going to be stacking one upon the other. And if you haven't practiced enough to get them all as they come at you, it can definitely be very overwhelming. All right, guys, that does it for the first part of lesson 3.2. I'll see you back here next time for the second part of the lesson. Thanks so much. Bye.